Now we're going to look at an example of a signal expansion. So we'll work through this example together. So we have this 3 by 3 image of numbers 1, 2, 3, 6, 7, 8, 3, 4, 5. And we want to write this image as a expansion of weighted and shifted 2D Kronecker delta functions. So let's start writing our expressions. So we have, say, S of m comma n. And the first thing we look at is at the origin has a value of 7. So we say 7 times delta m comma n plus, so let's take this term, that's 8. It's shifted 1 to the right, so that's delta m minus 1 comma n. Let's take this term here, and that's shifted the other way, so that's 6 delta m plus 1 comma n. And you can see that's got to be m plus 1 because this is m plus 1 equals 0 is where this Kronecker delta has its peak, and that happens at m equals minus 1. Okay, and let me just erase it. We're assuming that this is m and this is n. So since we're still in discrete notation. So then we can do this term here. So plus 4 delta, we're m because we're along m equals 0 axis, but then it's n minus 1 because we're shifted up 1. Look at this 2. So plus 2 delta m n plus 1. And then let's look at some of these diagonal terms. So this is 5 here. So that's plus 5 delta m minus 1 comma n minus 1. Let's look at this 3. So 3 delta m minus 1 n plus 1. And then we have another 3 over here. So that's plus 3. That's delta m plus 1 because it's shifted to the left there, and then n minus 1. And finally we have this 1 term, so that's just delta m, let's see, it's shifted over that way, so it's m plus 1 comma n plus 1. So that would be, the summation of all those terms would be our signal expansion using Kronecker deltas. Now, for continuous time, we have to use a different delta function, and that's called the Rect Delta function. And the notation here is instead of brackets, we have parentheses, and also we typically use a variable like x or t or something that is typically used for continuous time or space. So if we have a one-dimensional Rect Delta function, it's represented as delta of x. 2D would be delta of xy, or sometimes people use this to note it, but typically it's using some notation like this is fine. We can also do a 3D Rect Delta function, so delta x, y, z, or even an n-dimensional where we might represent the argument as a position vector. So the Rect Delta function is a rather unique function in the sense that it has these properties. It's equal to 0 everywhere except at the origin, and yet it has an area of 1. So the integral of the delta function is 1. So one way to think about this delta function is we could start off with a rect function. So for example, this is rect of x over tau with the amplitude of 1 over tau. Okay. And this has area of 1. So the area of this thing is equal to 1. And we imagine what happens as this tau gets smaller. So for example, here for this blue one, tau is equal to 1. Then here, tau equals 1/2. And here, tau equals 1/4. And so as we imagine making tau shrink to 0, this becomes infinitely large, so it goes up this way, and yet the width becomes infinitesimally small. And yet the area is equal to 0. In 2D, we have a similar picture where the Dirac delta function is equal to 0 everywhere except once again at the origin. And its integral over all space is equal to 1. And once again, we can consider the limiting case of an ordinary 2D function, which in this case is shown by this cube, which would have, for example, some base and some height, such that the area under this thing is equal to 1. And as we shrink the base, the height must go up to maintain that area. So the height has to go up. And then we continue this process where the height continues to increase while the base shrinks. And we look at the limit as that length goes to 0. Okay. A useful fact, which will come in very handy throughout the course, is that delta xy can be written, the 2D delta xy can be written as a product of delta x 1D times delta y. So it's a product of two 1D functions, and this is what's known as a separable function. Okay. So it's one type of separable function because it can be written as a product of an function x and a function in y. So one of the things that is important to note is that Dirac delta functions are not ordinary functions. Instead, they belong to a class of function called generalized functions. And so that means that they're really not defined by their value at any point. You can't really, for example, the origin, you really can't say what the value of the Dirac delta function is. So they're in fact more defined by what they do underneath an integral sign. And the most important property of the Dirac delta function is what's called the sifting property. And this is defined as follows. If I take a shifted Dirac delta function, so for example, this is a Dirac delta function with the origin at 0, at x is 0. So what it would look like is this. The way we represent it is, if this is the origin, we represent it as an impulse at x0, where this is x. And what it says is if I take that function, delta x minus x0, so this is delta x minus x0, and I multiply it by some function g of x, and then I integrate this product, then what I'm going to get out, the integral of the product, is exactly g of x 0. So what it does is it allows me to sift out or pull out the value of the function g of x at exactly x0. And to do this, we do have to assume that g of x is a smooth function. So for this course, we'll assume that g of x is sufficiently smooth. One way to sort of get an intuitive feeling for this sifting property is if you consider looking at any function g of x, say here, and here we've shown a smooth function, and multiplying it by a small rectangle function. And when we integrate the area, since the area is 1, then the integral of the area is simply going to be, so this, the delta function has an area of 1, and so when we multiply it by g of x, it's going to just make the area g of x 0. And so that's one way to look at the sifting function. So the sifting function is very useful because it means that we can represent any 1D function as this integral here. So any function g of x can be written as a shifted delta function multiplied by a weight at the place where the delta function is non-zero. And essentially we're adding up shifted delta functions with appropriate weights. So this is basically the same intuition as we had for Kronecker delta functions. It's just that now we have an integral sign here instead of summation, and we're dealing with a Dirac delta function. So the intuition is if you have any function g of x, you can approximate it with these very small rectangle functions, and then the approximation becomes increasingly accurate as you decrease the width of these rectangle functions such that they become delta functions. And so what you can maybe think about is that the limiting point, you're representing it as sort of all these little delta functions. Okay. We can do the same thing with a 2D function where here we have any function g of xy is equal to the shifted delta functions multiplied by their weight. And so here we have as an approximation, we can assume we have these two-dimensional functions of finite width and finite height. And in the limit, as these become small, then what we're going to end up with is that we're going to have these sort of shifted 2D delta functions. Okay? And so any function can be represented as the summation, or actually the approximation is the summation, but in the limit it becomes integrals of all these 2D delta functions.